Take a slow, deep breath in, and as you exhale, let your physical body settle completely into the soft support beneath you. Release the tension in your shoulders, unhinge your jaw, and allow the quiet of the night to surround you. Let your mind drift away from the confines of this room, floating upward and outward as we journey into the invisible, silent architecture of the cosmos, the curvature of space-time. In the year 1915, Albert Einstein published his groundbreaking theory of general relativity, forever changing how humanity perceives the force of gravity. Before this moment, gravity was imagined as a mysterious, invisible rope, a magnetic pull, dragging objects together across an empty void. But Einstein realized it was something far more beautiful and far more tangible. Gravity is not a pull. It is a geometric warping, a physical curving of space and time itself. To understand this, we must first look to the year 1908, when the mathematician Hermann Minkowski proposed that space and time are not separate entities. He conceptualized a four-dimensional continuum. There are three dimensions of space that you can physically navigate: up and down, left and right, forward and backward. And these are woven seamlessly together with one dimension of time. Imagine this fabric of space-time as a vast, silent ocean, perfectly smooth and flat in the deepest voids of the universe, waiting for something to rest upon it. Consider the bed beneath you right now. You can feel how your own physical mass creates a gentle, comforting depression in the mattress. The heavier the object, the deeper the depression. In the grand theater of the cosmos, our planet does exactly this. With a staggering mass of 5.972 times 10 to the 24th power kilograms, our pale blue world rests upon the invisible, yielding fabric of space-time. Its sheer weight creates a deep, smooth depression in the cosmic mattress. This slope, this geometric curvature, is the gravity well that gently holds the oceans to the seafloor, the atmosphere to the skies, and you to your bed. This invisible geometry creates the sensation of weightlessness. High above the Earth's surface, the International Space Station glides silently through the dark. Orbiting at approximately 17,500 miles per hour, the astronauts inside float with a serene grace, feeling completely weightless. Yet, they are not entirely free from Earth's gravity. Instead, they are simply in a state of continuous free fall along the curved geometry of space-time that Earth has created. They are moving forward so fast that as they fall down the slope of the gravity well, the curvature of the Earth curves away beneath them at the exact same rate. They endlessly miss the ground, coasting along the invisible contours of physics. You might wonder how this curvature interacts with the fastest thing in the universe, light itself. Visualize a single pure beam of starlight. The speed of light traveling in a perfect vacuum is a precise 299,792,458 meters per second. This absolute measurement is the ultimate cosmic speed limit. Even light, which we imagine as traveling in perfectly straight, unbending lines, must follow the physical contours of this space-time fabric. When light passes through a gravity well, its path curves. In physics, these natural paths are called geodesics. The straightest possible lines a massless particle can take across a curved surface. On the mild spring day of May 29, 1919, a total solar eclipse cast a shadow over the Earth, allowing the astronomer Arthur Eddington to prove this curvature for the very first time. As the moon perfectly blocked the blinding warmth of the sun, the sudden darkness of the sky revealed distant background stars that should have been hidden directly behind our star. Their light had journeyed for thousands of years, and as it grazed the massive gravity well of our sun, it gently bent along the curvature of space, wrapping around the sun to reach the telescopes on Earth. Eddington measured this delicate deflection angle at precisely 1.75 arc-seconds. It was a microscopic shift, but it exactly matched Einstein's mathematical prediction. In that quiet moment of shadow, humanity proved that space is malleable. But space-time is not just space, it is time. How does this curvature feel to you, here and now? It alters the very rhythm of reality. Imagine the steady, rhythmic ticking of an analog clock. Tick, tick, tick. Because gravity is the curving of both space and time together, time must stretch out where gravity is stronger. This means that a clock resting at sea level, deeper in Earth's gravity well, actually ticks at a slightly different rhythm than a clock placed high in the thin, freezing air of the mountains. At the snowy peak of Mount Everest, sitting at an elevation of 8,848 meters, you are further away from the densest part of Earth's gravity well, Chi. Because the curvature is ever so slightly flatter up there, time actually flows slightly faster. A clock on the summit of Everest moves faster than a clock on the beach by a fraction of a millisecond every year. As you lie still, feeling the solid ground foundation beneath your home, extending all the way down through the mantle to the molten iron core, consider this remarkable truth. Because gravity is more intense at the very center of the Earth, time moves slower there than it does here on the crust. Over our planet's vast 4.5 billion year lifespan, this relentless stretching of time has caused the inner core to age differently than the surface. The deep heart of the Earth is currently about 2.5 years younger than the surface you are resting upon. You are literally resting on top of the future, suspended above a younger past. We rely on this invisible stretching of time every single day. Floating far above the clouds, a network of GPS satellites orbits at an altitude of 12,550 miles. Up in that cold, silent expanse, they experience a much weaker gravitational pull from the Earth. Because of this flatter space-time, time moves faster for those satellites by approximately 45 microseconds every single day. If our scientists did not mathematically correct for this curvature of time, our global navigation systems down on the surface would drift off course by miles within a single day. The invisible math of the universe guides us home. Now, imagine the slow, majestic rotation of the Earth. As our planet spins in the silent vacuum, it doesn't just rest statically in the fabric of space-time, it drags the fabric along with it. Imagine taking a spoon and slowly turning it in a jar of thick, dark honey. The honey closest to the spoon twists and swirls. This beautiful phenomenon is called frame dragging, or the lens thirring effect. In the year 2011, after decades of planning, a highly sensitive satellite named Gravity Probe B finally proved that this twisting truly occurs. Using hyper-precise, supercooled gyroscopes, the satellite detected that Earth's rotation physically twists the local space-time around it at a rate of roughly 39 milliarcseconds per year. You are sleeping inside a slow, invisible whirlpool in the cosmic ocean. Space-time is not only a curved and twisting fabric, it is a medium that can ripple. Imagine the smooth, glass-like surface of a quiet pond at midnight. Picture a single cool droplet of water striking the center, sending perfect, concentric rings expanding outward. On September 14, 2015, the massive LIGO observatories detected the very first gravitational waves. These were literal ripples in the fabric of space and time, washing over our planet. These microscopic waves were generated by an event of unimaginable scale, the violent swirling collision of two black holes. Each of these ancient voids possessed about 30 times the mass of our Sun, and they were located an astonishing 1.3 billion light-years away. For 1.3 billion years, these invisible ripples traveled through the silent, empty void of the universe, expanding outward at the speed of light. When they finally passed through the Earth in 2015, they washed over your home, over your city, and over your own resting body. As the wave passed, it stretched and squeezed the actual physical space around you. And the amplitude of these waves was incredibly subtle by the time they reached our shores. They altered the 4-kilometer-long laser arms of the LIGO Observatory by a distance 10,000 times smaller than the width of a single proton. You could not feel it, you could not hear it, but it happened. The universe breathed, and the fabric of reality shuddered with the memory of a distant collision, vibrating like a plucked harp string in the dark. What happens when this curvature reaches its absolute mathematical limit? Picture the deep, tranquil center of a black hole. In 1916, the astronomer Carl Schwarzschild first calculated the mathematics of an infinitely deep gravity well. He conceptualized a point in space of infinite density, a place where the curvature of space-time never stops plunging downward. This point is known as a singularity. Surrounding this invisible point is a sphere of darkness called the event horizon. The event horizon is not a physical surface you could touch. It is simply a mathematical boundary. It is the exact threshold where the curvature of space-time becomes so steep, so profoundly deep, that the escape velocity required to leave it equals the speed of light. Because nothing in the universe can travel faster than 299,792,458 meters per second. Nothing that crosses this boundary can ever return. Not the heat of a dying star, not the brilliant flash of a supernova, not a single photon of light. It represents the universe's most perfect silence, a region of absolute undisturbed calm, suspended in the endless dark. Here, in the comfort of your own space, you are deeply connected to these grand mechanics. Your body, resting quietly, is a collection of matter, and therefore, you possess mass. Even now, your subtle mass is curving the space around you. You are your own tiny microscopic anchor in the fabric of reality, bending the cosmos simply by existing within it. The universe accommodates you. It yields to your presence. Allow yourself to feel the gentle embrace of gravity, not as a force holding you down, but as the soft, curving architecture of a universe that is holding you close. Long before humanity possessed the mathematical tools to measure the curvature of space-time, we stood beneath the glittering canopy of the night sky and searched for order in the dark. In the quiet observatories of antiquity, the human mind yearned to understand why things fall. Around the year 384 BC, the philosopher Aristotle proposed that objects moved simply because they were seeking their natural place at the center of the universe. For centuries, this poetic yet incomplete explanation satisfied our curiosity. The night sky was viewed as a perfect, unchanging sphere of fixed stars, rotating silently above a stationary world. The true mechanical rhythm of the cosmos began to reveal itself in the year 1687, when Isaac Newton published his monumental work, Principia Mathematica. Within those ink-stained pages, Newton formulated the universal law of gravitation, describing a universe governed by strict, predictable forces. He introduced the gravitational constant, a staggeringly small number known as g, which is exactly measured as 6.674 times 10 to the negative 11th power cubic meters per kilogram per second squared. Because this value is so incredibly weak, it requires objects of immense planetary scale, like our Earth, to generate a pull you can actually feel. Newton's mathematics perfectly predicted the arc of a cannonball and the orbit of the moon. Yet, he famously confessed that he had no idea what gravity actually was. He could describe its behavior, but the mechanism remained a profound, invisible mystery. Decades melted into centuries, and astronomers continued to track the slow, rhythmic waltz of the planets using Newton's laws. But a quiet anomaly emerged in the inner solar system, hiding within the blinding glare of the sun. In 1859, the French astronomer Urbain Le Verrier noticed something strange about the orbit of Mercury. Situated at an average distance of just 36 million miles from the solar surface, the Mercury is baked by intense heat and locked in a swift, elliptical journey. Le Verrier observed that Mercury's orbit was slowly rotating, a movement called precession. According to strict Newtonian physics, the gravitational tug of the other planets should cause a specific amount of rotation. However, Mercury's actual orbit was shifting by an unexplained extra 43 arcseconds per century. This tiny discrepancy, roughly 1/100th of a single degree every 100 years, baffled the scientific community. It was so confounding that astronomers hypothesized the existence of a ghost planet orbiting even closer to the Sun, entirely responsible for tugging Mercury off course. They named this hypothetical world Vulcan. For 50 years, stargazers scoured the horizons during solar eclipses, searching for Vulcan's shadow. It was never found, because it never existed. The ghost was not a planet. It was the curvature of space itself. When Albert Einstein finally applied his new geometric equations to Mercury, he found that the immense mass of the Sun creates a profound, steep valley in the fabric of space-time. Picture a heavy, polished glass funnel. Now, imagine rolling a single glass marble around the sloping inner rim of that funnel. The marble doesn't travel in a flat, perfect circle. The steep slope forces its path to slowly trace a spiral-like pattern, shifting slightly with every revolution. Because Mercury sits so deep within the Sun's gravity well, it rolls along this intensely curved slope. The geometry of that space perfectly accounted for those missing 43 arcseconds. The mystery was solved not by adding a new object to the sky, but by changing the shape of the sky itself. Observe how this hidden geometry orchestrates the grand rhythmic dance of our own solar system. In the year 1609, the astronomer Johannes Kepler published his revolutionary laws of planetary motion, proving that orbits are not perfect circles, but stretched shapes called ellipses. Every ellipse has two internal focal points. For the Earth, the Sun occupies one of these points, but the planets do not simply orbit a stationary sun. Instead, they engage in a mutual gravitational embrace centered around a balance point called a barycenter. Consider the colossal presence of Jupiter, a swirling sphere of hydrogen and helium gas, so immense that it possesses 318 times the mass of the Earth. Jupiter is so heavy that it significantly warps the local spacetime, pulling back against the Sun. Because of this massive tug-of-war, the true center of gravity, the barycenter, does not rest perfectly at the core of the Sun. Instead, it is located approximately 46,000 kilometers above the solar surface. As Jupiter slowly glides through its 12-year orbit, the Sun itself gently wobbles in a small circle around this invisible point in empty space. Everywhere you look in the cosmos, heavy celestial bodies are swaying in this slow, silent rhythm, gracefully navigating the depressions they create in the cosmic fabric. To truly map these invisible curves, humanity had to master the measurement of time. In 1656, the physicist Christian Huygens invented the pendulum clock, harnessing the steady swing of a weighted brass bob to track the passing seconds. It was a masterpiece of mechanical engineering. But to measure the delicate warping of time caused by gravity, we required something infinitely more precise. Enter the atomic age, where scientists rely on the quiet, microscopic heartbeat of the cesium-133 atom. Within a modern atomic clock, this specific isotope vibrates exactly 9,192,631,770 times per single second. This unvarying rhythm provides the ultimate steady baseline required to observe time stretching and compressing. In October of 1971, two physicists named Joseph Haffel and Richard Keating transformed the abstract concept of time dilation into an undeniable physical reality. They boarded commercial airline flights, carrying 4 highly sensitive synchronized atomic clocks, and flew twice around the entire world. High in the stratosphere, flying through the thin, cold air, the clocks were subjected to a slightly weaker gravitational field than those resting on the ground. When the planes finally landed, and the scientists compared the airborne clocks to the stationary master clock at the U.S. Naval Observatory, the numbers spoke for themselves. The clocks that traveled eastward had literally lost 59 nanoseconds of time, having aged slightly less than the clocks left on the ground. This microscopic discrepancy verified that as we move through different altitudes and velocities, we are physically traveling through different densities of time. At a more localized scale, this identical principle was tested vertically inside a quiet, unassuming brick structure at Harvard University. In 1959, the Pound-Rebka experiment measured a phenomenon called gravitational redshift. Within the enclosed shaft of the Jefferson Physical Laboratory Tower, physicists created a perfectly vertical drop of exactly 22.5 meters. At the top of the tower, they placed a sample of the radioactive isotope iron-57, which naturally emitted a steady stream of high-energy gamma rays down the shaft. As these invisible rays of light plunged downward, falling deeper into Earth's gravity well, the light absorbed energy from the gravitational field. Because the speed of light is completely rigid and cannot increase, the light had to express this extra energy by changing its frequency. By the time the gamma rays hit the detector at the bottom of the 22.5-meter drop, their frequency had increased, shifting ever so slightly toward the blue end of the electromagnetic spectrum. The change was impossibly small, a fractional shift of exactly 2.5 times 10 to the negative 15th power. Yet, it was captured perfectly by the instruments. In the quiet darkness of a brick tower, humanity observed the color of light physically altering as it slid down the microscopic slope of Earth's gravity. When we turn our modern gaze outward, scaling up from a brick tower to the edge of the observable universe, we witness this same geometric bending on a scale of unfathomable majesty. In 1979, astronomers studying a distant object known as the twin quasar made a stunning discovery. Officially designated as QSO 0957 plus 561, this brilliantly glowing core of an ancient galaxy resides an astonishing 8.7 billion light-years away from Earth. Through their telescopes, astronomers saw what appeared to be 2 identical, brightly burning quasars sitting right next to each other. In reality, there was only one. Between us and that distant quasar sits a massive, intervening galaxy. The immense mass of this middle galaxy bends the fabric of space so severely that it acts as a cosmic magnifying glass. As the ancient light from the quasar journeyed toward Earth, it hit this gravitational curve and split into two separate paths, traveling around both sides of the intervening galaxy. This process, known as gravitational lensing, caused the light to arrive at our telescopes from two slightly different angles, creating a perfect optical illusion of a double star. Today, telescopes routinely photograph distant galaxy clusters, such as the massive cluster known as Able 2218. When you look at an image of this region, 1-2, you do not just see the bright white and yellow spheres of foreground galaxies. Wrapping around them, tracing the invisible contours of space-time, are highly distorted, sweeping arcs of vibrant orange and sapphire blue light. These arcs are the smeared, stretched images of background galaxies located billions of light-years further away. Their light has been beautifully warped by the sheer weight of the galaxies in front of them. The universe itself operates as a grand, curving lens, bending ancient starlight into elegant, sweeping brushstrokes across the dark canvas of the void. Every discovery, from the quiet swinging of a pendulum to the distorted amber light of a distant quasar, tells the same enduring story. We are suspended within a dynamic, responsive architecture. The cosmos is not an empty, static room where events simply happen. It is an active, yielding participant in the grand mechanics of reality. As the Earth glides along its orbital track, and as distant galaxies warp the ancient light of the void, the universe continues its slow, majestic unfolding. As we observe this slow, majestic unfolding, we find that the geometry of the universe is rarely perfectly smooth. We often imagine celestial bodies as flawless, mathematically perfect spheres, creating perfectly uniform slopes in the fabric of space. But reality is far more textured. Picture our own Earth. It is not a perfect sphere, but rather an oblate spheroid. Because our planet rotates constantly, centrifugal forces cause it to bulge outward at the equator. This means the Earth is approximately 43 kilometers wider across its midsection than it is from pole to pole, Doris. Because the physical mass of the planet is unevenly distributed, the depression it creates in space-time is equally varied, mapped with subtle hills and shallow valleys of gravity. To measure these delicate, invisible variations, scientists launched the Gravity Recovery and Climate Experiment, known as the GRACE mission, in March of 2002. Picture two identical metallic satellites quietly orbiting the Earth in tandem, flying exactly 220 kilometers apart. They are connected not by a physical tether, but by a continuous, highly precise beam of invisible microwave energy. As the lead satellite flies over a region of the Earth with slightly more mass, such as a dense mountain range or a deep ocean trench, the local gravity well is fractionally deeper. This extra curvature gently pulls the first satellite forward, briefly increasing the distance between the two spacecraft. The instruments aboard the GRACE satellites were so profoundly sensitive that they could measure a change in their separation distance down to 10 micrometers. To put that into perspective, 10 micrometers is roughly 1/10 the width of a single human hair. Through this microscopic tracking, we discovered that the physical curving of space-time around our planet changes continuously with the seasons. For instance, researchers calculated that the continent of Antarctica loses an average of 150 billion metric tons of ice every single year. As this unfathomably heavy sheet of frozen water melts and disperses into the global ocean, The local mass of the continent decreases, and the gravity well beneath it subtly flattens out. Consider how this relates to a familiar, comforting object in your own life. Imagine resting in a brightly woven fabric hammock on a warm afternoon. As you shift your body weight, pulling your knees up or stretching your arms out, the tension of the individual threads instantly responds. The shape of the hammock continually redistributes itself to perfectly cradle your new position. Space-time behaves in exactly this same accommodating manner. It is not rigid or unforgiving. It is a highly responsive medium, continuously adjusting its curvature to cradle the shifting oceans and melting glaciers of our world. This responsive geometry doesn't just hold matter, it dictates the flow of energy. In 1964, the astrophysicist Erwin Shapiro proposed a brilliant new method to test the yielding nature of the cosmos, which we now call the Shapiro time delay. He realized that if gravity truly warps the fabric of space, then a beam of light passing through a gravity well would have to travel a physically longer distance, dipping down into the curvature and climbing back out. To prove this, scientists transmitted powerful radar pulses from Earth, aiming them directly at the rocky surface of Venus. They waited for a specific celestial alignment known as superior conjunction, a moment when Earth and Venus are on opposite sides of the Sun. During this alignment, the radar signals had to graze the intense, sloping gravity well of our nearest star before bouncing off Venus and returning home. When the signals returned, the recording instruments showed they were delayed by roughly 200 microseconds compared to what strictly flat Newtonian space would predict. Think of this journey as if you were walking along a dry, smoothly paved sidewalk, moving at a brisk, uninterrupted pace. Suddenly, the path slopes downward and leads you into a waist-deep, slow-moving river. As you push through the water, the thick, heavy medium physically resists your forward motion, extending the time it takes you to reach the other side. When the radar pulse entered the deep curvature of the Sun's mass, it was as if the light waded through a cosmic river. The space-time was so stretched that the light required physically more time to cross it. The universe slowed the light down, embracing it in the gentle resistance of gravity. Deep within our galaxy, this stretching and curving takes on a rhythmic, almost musical quality. In 1974, astronomers Russell Hulse and Joseph Taylor pointed the massive radio dish of the Arecibo Observatory toward the constellation of Aquila. There, they discovered a mesmerizing celestial mechanism, the very first binary pulsar, officially cataloged as PSRB 1913+16. A pulsar is a type of neutron star, the incredibly dense, glowing core left behind after a massive star exhausts its fuel and collapses. Notice how extreme the geometry of a neutron star truly is. Each of the two stars in this binary system contains about 1.4 times the total mass of our Sun. Yet, this staggering amount of matter is compressed into a sphere merely 20 kilometers in diameter. Imagine gathering every single skyscraper, every mountain range, and every drop of ocean water on Earth, and systematically compressing them under immense pressure until the entire planet could fit comfortably inside a silver thimble. The gravity wells these hyperdense stars create are incredibly steep, resembling deep, sharp punctures in the fabric of space-time. These two dense thimbles of matter are locked in a relentless, beautiful waltz, completing a full orbit around each other every 7.75 hours. But they are not moving through empty space. They are churning the space-time fabric around them. Because their gravitational pull is so extreme, their rapid movement generates ripples of energy that radiate outward into the void. As they emit these waves, the system slowly loses energy, causing the two stars to draw closer together. Meticulous measurements revealed that their orbit shrinks by precisely 3.15 millimeters every single year. Picture the delicate rhythmic mechanics of a vintage phonograph. When you carefully place the metal needle onto the outer edge of a heavy vinyl record, it catches the groove. As the record spins in a continuous, smooth rotation, the needle tracks the subtle indentations, slowly and inevitably spiraling inward toward the center label. The binary pulsars of PSRB 1913 plus 16 are tracing an identical inward spiral along the curved grooves of spacetime. This microscopic 3.15 millimeter orbital decay perfectly matched the energy loss predicted by general relativity. It was the first indirect proof that the universe can ripple, a discovery so profound it earned Hulse and Taylor the Nobel Prize in Physics in 1993. At this very moment, in even more extreme environments, this curvature creates brilliant, swirling displays of color and heat. When a massive black hole pulls surrounding gas and dust into its steeply sloped gravity well, the material does not fall straight down. Instead, it spirals inward, forming a wide, luminous ring known as an accretion disk. The gravitational forces at the inner edge of this disk are so intense that the hydrogen and helium gases are whipped up to tremendous speeds, traveling at nearly 10% the speed of light. As the gas particles collide at these blistering speeds, immense friction is generated. The gas physically heats up to a staggering 10 million degrees Celsius. At these extreme temperatures, the matter transitions into a glowing plasma, emitting brilliant high-energy X-rays. Astronomers regularly detect a very specific signature radiating from these disks, known as the iron K-alpha line, which registers exactly at 6.4 kilo-electron volts on our spectrographs. Imagine observing a quiet evening campfire. If a sudden, steady breeze catches the glowing orange embers, they are swept up into a tiny spinning vortex. As they swirl faster in the oxygen-rich air, they burn brighter, transitioning from a dull red to an intense, brilliant white. An accretion disk is the universe's ultimate spinning ember, glowing with the fierce heat of friction as it skirts the very edge of the deepest curves in existence. Yet, even in the presence of such profound heat and velocity, the mechanics of spacetime remain entirely orderly. The extreme curvature near the black hole creates an optical phenomenon known as Doppler beaming. As the accretion disk spins, the luminous gas moving rapidly toward our telescopes on Earth appears intensely bright and is shifted toward the blue end of the light spectrum. Conversely, the gas spinning away from us on the opposite side of the disk appears much dimmer, its light stretched into longer, redder wavelengths. The curvature of space acts as a prism and a lens all at once, painting the void with shifting asymmetric halos of light. Every mountain range on our world, every radio pulse echoing through the dark, and every swirling disk of superheated plasma is bound by these same geometric rules. The universe operates on a spectrum of curvature, from the gentle, accommodating dip of a melting glacier to the severe, spiraling plunge of a binary pulsar. You are nestled within this vast, mechanical symphony. The same physics that orchestrate the slow decay of distant stars also shape the gravity that holds the atmosphere against the quiet night sky above you. As we pull our focus back from the swirling, superheated plasmas of distant star systems, we find that the grand geometry of the universe is intimately woven into your own personal existence. The physics that guide a distant galaxy are the exact same mechanics pressing softly against you right now. You are an active participant in this cosmic architecture. Reflect on the physical sensation of your body resting. You feel a gentle, constant weight anchoring you to the cushions beneath you. In the year 1907, Albert Einstein sat in a quiet patent office in Bern, Switzerland, and experienced what he later called his glücklicher Gedanke, his happiest thought. He realized that a person in a free-falling elevator would not feel their own weight. From this simple, profound idea, he developed the equivalence principle. This principle dictates that the local effects of a gravitational field are entirely indistinguishable from the physical sensation of constant acceleration. To understand this, picture yourself sitting comfortably in a perfectly sealed, completely silent train car, suspended in the vacuum of deep space. If this train suddenly began to accelerate forward at a smooth, steady pace, your body would naturally press back into the soft upholstery of your seat. The floor of the train would push against your feet because the Earth's mass creates a depression in the fabric of space-time. Resting on the surface of our planet feels mathematically identical to accelerating upward at a constant rate of 9.8 meters per second squared. The mattress beneath you is not merely supporting your weight. In the language of pure physics, the curvature of space-time is gently and continuously accelerating the ground up to meet you. This personal relationship with the cosmos extends even to the flow of your own biological age. Because you live your life within this gravitational slope, your physical body is stretched across different microscopic zones of time. In the year 2010, researchers at the National Institute of Standards and Technology, or NIST, set out to measure this intimate warping. They constructed incredibly precise quantum logic clocks, utilizing a single supercooled ion of aluminum-27. And this solitary atom was trapped in an electromagnetic field, its natural vibrations oscillating at over 1 million billion times per second. Scientists placed 2 of these immaculate clocks in the same laboratory, altering their vertical heights by a mere 33 centimeters, just over 1 single foot. Even across this incredibly small distance, the clock positioned 33 centimeters higher ticked measurably faster because it was ever so slightly further away from the dense center of Earth's gravity well. Applying this exact metric to the human form reveals something extraordinary. Because your head is generally further from the center of the Earth than your feet, time moves slightly faster for your mind. Over an average human lifespan of 79 years, your face will physically age about 90 billionths of a second faster than your toes. Your very cells are moving through the 4th dimension at different speeds, harmonizing with the invisible curves of the world. Deep within the darkest, deepest space-time depressions, this geometry does more than alter time. It actively forges the materials that make up your body. Consider the profound, crushing gravity well at the center of our solar system. The mass of the sun bends space so severely that the pressure at its core reaches unfathomable extremes. Here, the temperature burns at a steady 15 million degrees Kelvin. This intense, gravity-driven pressure cooker forces hydrogen atoms to collide and fuse together in a sequence known as the proton-proton chain reaction. At this exact moment, the sun's core is converting approximately 600 million metric tons of hydrogen into helium every single second. And this massive nuclear fusion generates an incredible outward pressure of radiation and thermal energy. Yet, the star does not explode. It remains in a state of perfect, serene balance, called hydrostatic equilibrium. The outward push of the nuclear fire is perfectly contained by the inward curving slope of space-time, pulling the mass together. This delicate balance of geometry and energy has bathed our planet in warm, steady light for billions of years. When you trace the origins of your own biology, you find that the elements forming your bones and blood required even steeper gravity wells to exist. Every single molecule of carbon in your cellular structure, the fundamental building block of all known life, was created by an incredibly specific cosmic coincidence called the triple alpha process. In 1952, the brilliant astrophysicist Fred Hoyle mathematically proved how this process works. He calculated that deep inside the cores of dying red giant stars, 3 separate helium-4 nuclei must collide almost simultaneously to fuse into a single atom of carbon-12. This rare fusion cannot happen in the relatively mild conditions of our Sun. It requires an astonishing temperature of 100 million Kelvin to overcome the natural electrostatic repulsion between the helium atoms. Only the immense, crushing gravity of an aging, massive star can bend space-time deeply enough to generate this specific heat. The carbon in your DNA, the oxygen in your lungs, and the iron coursing through your veins were all synthesized inside these steep, ancient funnels of gravity. You are a biological manifestation of curved space. Eventually, when those ancient massive stars exhausted their nuclear fuel, the outward pressure of fusion ceased. The delicate hydrostatic equilibrium was broken, and the star's outer layers collapsed down the steep gravity well at immense speeds, rebounding off the dense iron core. This colossal rebound triggered a supernova, a silent, brilliant explosion that scattered these newly forged elements across the interstellar vacuum at speeds exceeding 30,000 kilometers per second. Roughly 4.6 billion years ago, a drifting cloud of this stellar debris slowly began to gather, coaxed together by its own collective gravity. As the dust particles and gases accumulated, their combined mass gradually deepened the local curvature of space-time, pulling in more material until our swirling blue planet was formed. Notice how precisely tuned our world is to support your existence. The Earth possesses a total mass of 5.972 times 10 to the 24th power kilograms. This specific amount of matter creates a gravity well with an escape velocity of exactly 11.2 kilometers per second. If an object or a molecule of gas is not traveling at least 11.2 kilometers per second, it cannot climb out of the space-time depression Earth has created. This mathematical threshold is deeply comforting. It means that the delicate, life-giving mixture of 78% nitrogen and 21% oxygen in our atmosphere does not have enough kinetic energy to escape into the void. The invisible curvature of the cosmos forms a protective, transparent bowl, holding the breathable air close to the surface, allowing forests to breathe and oceans to absorb carbon. If the Earth were significantly less massive, like the planet Mars, the gravity well would be too shallow, and our atmosphere would slowly bleed away into the cold, silent vacuum. We are held perfectly safe by this geometry. The universe is not a chaotic, unpredictable void. It is a meticulously balanced system of curves, balances, and slow, majestic cycles. The iron in your blood remembers the profound gravity of ancient stars, and the subtle weight of your body shapes the mattress beneath you in the same way the Earth shapes the solar system. The rhythm of your breathing aligns with the slow, steady clockwork of a cosmos that has spent billions of years preparing a quiet, stable place for you to rest. Resting in this quiet stability, you might wonder about the physical texture of the space extending far beyond your walls. We often imagine the deep vacuum of the solar system as completely sterile, an endless, scentless dark. Yet, when astronauts return to the pressurized airlocks of the International Space Station after a long spacewalk, They report a very specific, lingering aroma clinging to their woven heavy suits. As they remove their helmets, they consistently describe a sharp metallic scent, heavily compared to seared steak, hot metal, and the bitter tang of welding fumes. To understand why the cosmos carries this distinct fragrance, we look to complex microscopic structures called polycyclic aromatic hydrocarbons, or PAHs. These incredibly resilient carbon-based molecules are forged in the intense, curved pressure cookers of dying stars and forcefully expelled into the interstellar medium. They float silently through the cosmic valleys, carrying the burnt aromatic memory of ancient stellar fires all the way to the fabric of our orbital stations. Even in the near-perfect vacuum of space, the geometry of the universe retains the sensory ashes of its history. The physical temperature of this space-time geometry provides another sensory marvel. Far away from the warming, radiating glow of any star, the deepest pockets of the universe are profoundly cold, but they do not quite reach absolute zero. Instead, the fundamental baseline temperature of the cosmos sits at exactly 2.725 Kelvin, which translates to a freezing minus 270.425 degrees Celsius. Scientists discovered the source of this faint, persistent warmth in the year 1964. Radio astronomers Arno Penzias and Robert Wilson were meticulously calibrating the massive horn-shaped Holmdel antenna in Holmdel, New Jersey. No matter where they pointed their delicate supersensitive instrument into the sky, they detected a constant, low-frequency microwave hiss. What they were hearing was the cosmic microwave background, the oldest light in existence, released into the void roughly 13.8 billion years ago during the fiery infancy of the universe. When this ancient light was first emitted, the entire cosmos was a blistering opaque plasma, glowing with intense, high-energy ultraviolet radiation. So, why do we measure it today as a cold, invisible microwave? This brings us to a profound characteristic of space-time. It is not a rigid container. It is an active, stretching medium. Picture an antique, intricately woven silk tapestry mounted on a massive, slowly widening loom. As the wooden frame of the loom pulls outward, the individual silk threads of the tapestry are dragged farther apart, stretching the image woven into them. As those ancient ultraviolet photons traveled across billions of light years, the actual physical space beneath them expanded. This stretching physically lengthened the light waves, a process known as cosmological redshift. Over eons, the light's color smoothly shifted. It cooled from a blinding violet, down into a soft blue, faded into a warm yellow, deepened into a dark, rich crimson, and finally stretched so far that it dropped off the visible spectrum entirely. It became the invisible, gentle microwave radiation that bathes the Earth and your resting body at this very moment. The universe is literally cooling its colors by expanding the canvas they are painted upon. In the era of analog televisions, when you tuned to an empty channel, the screen filled with a chaotic, hissing black and white static. Approximately 1% of that visual and auditory noise was the direct interception of this 13.8 billion-year-old light. You were watching the cooled, stretched remnants of creation dancing across a glass tube. At this very moment, this stretching process is actually accelerating. In 1998, two independent teams of astrophysicists were studying the light from distant dying stars, known as Type 1a supernovae. These specific explosions are utilized as flawless cosmic measuring tapes because they always detonate at a precise mass threshold, known as the Chandrasekhar limit, which is exactly 1.44 times the mass of our Sun. because their explosive brightness is a known rigid constant. Astronomers could measure exactly how far away they were by observing how dim they appeared. They found that the light from these ancient supernovae was much dimmer than the standard laws of constant expansion predicted. The universe is accelerating outward, driven apart by a repulsive pressure inherent to the vacuum of space itself. We call this phenomenon dark energy. According to the highly detailed maps generated by the Planck Space Observatory, this invisible stretching energy accounts for precisely 68.3% of the entire energy density of the universe. Space-time is pushing itself apart in all directions, creating more empty, silent volume with every passing second. While the grand cosmos expands, local pockets of intense gravity create a fascinating tightening effect. Deep within the gravity well of our sun, space is physically cinched inward, a geometric tightening called the geodetic effect. If you could lay a physical measuring tape perfectly around the entire circumference of Earth's orbital path, flat Euclidean mathematics dictates it should be exactly 2 times pi times the radius. However, because the immense mass of the sun pinches the space-time fabric inward, the actual physical circumference of our orbit is about 2.8 centimeters, just over 1 single inch, shorter than flat math predicts. A tiny sliver of physical space is simply missing, gently folded into the steep curve of solar gravity. Closer to home, the curvature of space dictates the rhythmic, soothing breathing of our oceans. Observe how our moon, a rocky sphere with a mass of 7.347 times 10 to the 22nd power kilograms, orbits at an average distance of 384,400 kilometers from Earth. Even from that staggering distance, the gentle slope of its gravity well reaches out and touches our planet. But the slope is not perfectly even. To understand the mechanics of the tides, we must look at differential gravity. The gravitational pull from the moon is physically stronger on the side of the Earth facing it, and measurably weaker on the far side. This difference in curvature creates a stretching sensation across the entire 12,742 kilometer diameter of our planet, a gradient known as tidal force. This unequal geometry gently pulls the liquid oceans away from the solid crust, causing the water to bulge outward into an ellipsoid shape. As the Earth slowly rotates through these gravitational bulges, we experience the predictable calming rise and fall of the sea. In coastal regions like the Bay of Fundy in Canada, the local funnel-like geography naturally amplifies this geometric stretching, resulting in massive, rhythmic tidal shifts of up to 16 meters, or roughly 53 feet, every single cycle. Every time you listen to the steady, rhythmic crash of cold, frothing surf against wet sand, you are hearing the sound of millions of gallons of water sliding up and down the invisible, shifting slopes of lunar gravity. To comprehend the ultimate physical texture of this yielding fabric, we must look unimaginably close. In 1955, the theoretical physicist John Archibald Wheeler proposed that if you zoom in far enough, space-time completely loses its smooth, continuous nature. At the microscopic scale of the Planck length, which is an infinitesimally small 1.6 times 10 to the negative 35th power meters, the mathematics of gravity break down into utter, roiling chaos. Wheeler called this microscopic texture the quantum foam. At this impossible resolution, the concepts of space and time are bubbling, frothing, and fluctuating with violent quantum energy. Miniature wormholes and microscopic gravity wells snap into existence, curve sharply, and vanish completely within fractions of a nanosecond. The very foundation of reality is a boiling, hyperactive sea of probabilities. Yet, from our macroscopic perspective, billions of times larger than the churning quantum foam, all of this microscopic boiling perfectly averages out. It smooths into the quiet, highly predictable geometry that holds the moon in its orbit. It captures the atmosphere against the sky and keeps you resting firmly and safely in your bed. The universe rests upon a roaring ocean of microscopic energy, but to you, it presents only the calm, glassy surface of a silent starlit lake. Allow your awareness to float on this still surface, suspended in the perfect balance of cosmic architecture. As our observation of the cosmos gently slows, we bring our focus back from the outermost edges of the universe to the immediate physical world currently cradling you. What's happening now is a continuous invisible interaction between the celestial sphere and the solid ground beneath your home. We commonly think of gravity's rhythm as a force that only affects the liquid oceans, but the rocky crust of our planet is also incredibly pliable over massive distances. Scientists discovered a profound geological phenomenon known as solid earth tides. Through meticulous measurements utilizing global positioning systems and highly sensitive tilt meters, geophysicists determined that the actual bedrock of the continents rhythmically rises and falls twice every single 24 hours. The process unfolds gradually over 12-hour increments. First, as the moon slowly aligns with your specific longitude in the night sky, the invisible slope of its gravity well reaches down. Second, this gradient pulls gently but relentlessly on the massive tectonic plates. Third, the silicates, basalts, and granites of the Earth's crust elastically deform under this tension. This stretches the ground upward by a maximum of 55 centimeters, or roughly 22 inches, at the planet's equator. As the moon continues its orbit and the Earth rotates past this alignment, the crust slowly and softly settles back into its baseline shape. You do not feel this subtle, microscopic elevator ride, but you are physically partaking in a slow, planetary respiration, rising and falling with the silent mechanics of the void. Deep within the darkest regions of the universe, even the most extreme distortions of space-time eventually undergo a similar process of returning to perfect flat calmness. For decades, astrophysicists believed that a black hole was a permanent, inescapable puncture in the cosmic fabric, an eternal scar on the geometry of space. However, in 1974, the theoretical physicist Stephen Hawking demonstrated mathematically that these massive objects slowly evaporate. When the process is a masterpiece of quantum mechanics interacting with geometric curvature, playing out over unfathomable stretches of time. Step by step, this cosmic erasure unfolds. Right at the mathematical boundary of the event horizon, the vacuum of space is not truly empty. It is brimming with fluctuating quantum energy. Pairs of virtual particles, one particle and one antiparticle, constantly pop into existence, briefly separate, and annihilate one another in fractions of a single microsecond. When this microscopic dance occurs precisely on the steep, severe slope of a black hole, the intense gravity permanently separates them. It pulls one particle down into the dark, while providing the other particle with just enough energy to escape into the wider universe. This escaping particle is known to modern science as Hawking radiation. Because the black hole loses a microscopic fraction of its total mass with every single escaping particle, its gravity gradually becomes shallower. For a black hole possessing the mass of our Sun, this evaporation process requires an incomprehensible timescale of 10 to the 67th power years. In the ultimate display of cosmic patience, the severe depression in space-time flattens out, inch by infinitesimal inch, millennium after millennium. The mass radiates away as gentle, warming energy until perfectly smooth, undisturbed space is entirely restored. The universe always seeks balance, eventually smoothing away even the deepest extremes of gravity. Picture this journey on a much more intimate, personal scale. The material reality of your physical form is the direct result of a multi-billion-year process orchestrated by these curving, intersecting pathways of space. To assemble the delicate cellular structure currently resting in your bed, the universe had to forge specific heavy elements and transport them across the freezing dark. Your body is composed of highly specific atomic ratios. By mass, you are exactly 65% oxygen. Carbon constitutes roughly 18.5% of your form, while hydrogen accounts for 9.5%. Every single atom of that carbon and oxygen was fused inside the blinding nuclear furnace of a massive star over 5 billion years ago. When that ancient star collapsed and rebounded in a brilliant supernova, it ejected these newly forged elements outward at speeds exceeding thousands of kilometers per second. The process of delivering them to this exact moment was guided entirely by the curvature of spacetime. The atoms drifted endlessly through the interstellar medium, following the gentle slopes created by passing star clusters. The dust particles cooled in the absolute zero of the void, slowly gathering in a quiet, dark molecular cloud. Step by step, over millions of years, the collective mass of the accumulating dust deepened the local space-time depression, pulling the particles closer and closer together until they ignited to form our sun. From the spiraling, flattened disk of leftover debris, the universe gathered the building blocks of your existence, the iron that now constitutes exactly 4 grams of your body mass, specifically tailored to bind with oxygen inside your human blood, was folded into the molten core of the early Earth. The universe physically curved space to shepherd these specific elements across the galaxy, coalescing them into the water you drink, the air you breathe, and the bones that support you. You are ancient stardust, woven together by the slow, patient hands of gravity. Notice how your own biology continuously responds to yielding to this invisible slope. As you lie completely horizontal, a magnificent physiological process begins, dictated entirely by the physics of your posture within Earth's gravity well. Throughout the waking day, while standing or sitting upright, your cardiovascular system must continuously work against the 9.8 meters per second squared of downward acceleration. Your heart pumps against the vertical curvature of spacetime to push heavy, iron-rich blood upward into your brain. Now, in a resting, horizontal position, see, that physical resistance is completely neutralized. First, your baroreceptors, specialized pressure sensors located in your blood vessels, detect that the gravitational load has equalized across your entire body. Second, they send chemical signals to your autonomic nervous system to reduce the effort of your heart. Consequently, your resting heart rate drops by an average of 10 to 15 beats per minute. Your blood pressure safely and steadily lowers, requiring far less energy to circulate vital oxygen to your fingertips and toes. Simultaneously, the absence of vertical gravitational compression initiates a structural, restorative process in your skeletal system. Between each of your 33 individual vertebrae sit highly specialized intervertebral discs filled with a thick gel-like substance. Throughout the day, gravity gently squeezes these discs, expelling trace amounts of water. Now that you are resting parallel to the Earth's surface, the osmotic pressure reverses. Step by step, the discs slowly reabsorb ambient fluid from the surrounding cellular tissues, plumping up like dry sponges placed in cool water. By the time morning arrives, this gravitational respite will have physically lengthened your spine, making you approximately 1 to 2 centimeters taller. Your body is actively repairing itself, expanding and healing, simply because you have surrendered to the geometric curvature of the planet. The cosmos has prepared this quiet sanctuary for you. The planets continue their rhythmic, unending orbits, tracing elegant ellipses along the warped pathways of the solar system. The galaxies spin in the deep cold of the void, their ancient, fuse-colored light bending gracefully around invisible obstacles. Every mechanical movement in the heavens is operating with perfect silent precision, requiring no effort, no thought, and no attention from you. Permit the mind to quiet its searching. Allow the muscles to completely soften, heavily and willingly surrendering to the gentle pull of the earth. Release the need to hold yourself up. The solid ground is here. The grand structure of the universe is supporting your weight. You are held securely by the invisible, accommodating fabric of reality. Your breathing naturally mirrors the slow, gentle expansion of space. Inhaling calm, exhaling the remnants of the day. Every heavy element in your physical form is safely anchored to the beautiful blue planet that formed it. There is nowhere else you need to travel, and there is nothing else you need to compute. The curvature of space-time cradles you in an endlessly protective embrace. You are entirely safe within the comforting void. You are a quiet, peaceful observer of the night, resting deeply in the grand design of physics. The ancient stars are watching over the dark. The distant galaxies are resting in their slow, majestic rotations. You are melting perfectly into the warmth of your own gravity, fading into the peaceful silence. Good night.